Again, this is a review from grade 11, drawing free body diagrams. They will help you with the forces unit, which is where we're looking at here. Free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. A free body diagram is a special example of the vector diagrams that were discussed earlier. These diagrams will be used throughout our study of physics. The size of the arrow in a free body diagram reflects the magnitude of the force. In English, what does that mean? The longer the arrow, the stronger the force. Big forces, big arrows. Teeny tiny forces, teeny tiny arrows. The direction of the arrow shows the direction that the force is acting. Each force arrow in the diagram is labeled to indicate the exact type of force. It's generally customary in a free body diagram to represent the object by a box and draw the force arrow from the center outward in the direction that the force is acting. Here's an example right here. Again, it's customary to draw them away from. So here we have an FAPP. What do you think FAPP stands for?
Applied.
Applied force, exactly. I like to just write that as FA, the applied force. Could there be more than one force applied?
Yep.
Sure. How would you label them if there was 3 applied forces?
3 arrows.
Yeah, but how would you label them? FA1, FA2, FA3. Or you can call them Alice, Bob, and Carol. I don't really care. Maybe, depending on what's happening in the situation. It's not a hard and fast rule. What does F grav refer to here in our world?
Weight force.
Weight force, very good. Force of gravity. F norm, normal force, right? That's the table holding it up, force. And F fric, well, that's pretty obviously, I call it FF, right? Friction force. The big F stands for force, and then the subscript stands for what kind of force, right? All kind of review, right? I don't know what you guys that did grade 11, Mr. Smigalski, but I imagine it was pretty similar. Yes, Mandy? Is it sort of the same? No? Free body diagram above depicts 4 forces acting upon an object. Objects do not necessarily always have 4 forces acting upon them. There will be cases in which the number of forces depicted by a free diagram will be 1, 2, or 3. Is there ever a case where there could be 0 forces, Quinn? Could you ever have an object with 0 forces acting on it? It would have to be in like interstellar space, so far away from any other object that there's basically no gravity. Yes. Did that sort of blow your mind watching Interstellar? Yeah, I was confused. Yeah. The only rule for drawing free body diagrams is to depict all the forces that exist for the object in that given situation. Thus, to construct free body diagrams, it's extremely important to know the various types of forces. If given a description, begin by using your understanding of the force types to identify which forces are present. Then determine the direction in which each force is acting. Finally, draw a box and add arrows for each existing force in the appropriate direction. Label each force arrow according to this type. If necessary, refer to the list of forces and their description in order to understand the various types of forces. Okay, so practice. Hopefully some of you tried this. Okay, if you didn't, you got to ask yourself, how come I didn't do this? At least try it. You might say, oh, I don't know how to do this. But you can try. At the very least, you could have drawn a box for each one. You got to try it. A book is at rest on the tabletop. Diagram the force acting in the book. Weight force down. Normal force up, right? In fact, let me just see here. I think I can do this, so I don't have to draw them all. Oh, that's more practice. You guys have an answer one on yours, don't you? Here it is here. Boy. Here we go. This way I can just click on it. Oh, it's going to do that. Okay, here's the answers here. So there's the first one. Here's the second one here. A girl is suspended motionless from the ceiling by 2 ropes. Here's the free body diagram. We got gravity down, and they got 2 forces, each labeled F10s.
What's that mean again?
Tension. I would have called them FT, or I don't see any reason why you can't call them applied force 1 and applied force 2. It's a tension in a rope, right? Why are there two of them? Two ropes. Do you see that these arrows here are shorter than this one? But if you were to add these two together, you should get the same as that one, right? How come? Suspended motionless, no acceleration. Oh, good one. Got it. Egg is free falling from a nest in a tree. There it is there.
Go up.
This one here. Why is there just one?
It's falling.
It's falling, gravity's pulling down, it says neglect air resistance. In other words, don't include air resistance. So it's just that one there. Zach, is this object accelerating?
Yes,
How can you tell?
there's only one force.
Could it be accelerating if there's two forces?
Could be.
Could-
They weren't equal.
If they weren't equal, very good. In this case here, you're right, there's only one that's accelerating. This time we have a flying squirrel is gliding, there's no wing flap from tree to the ground, at a constant velocity. That's a key word there, because what does it mean? It means the acceleration is zero, which means the forces are equal or balanced, and that's what they have here. They have air resistance balanced by gravity. Again, this is a review from grade 11. Here we have number 5, a rightward force applied to a book in order to move it across the desk with a rightward acceleration. Rightward acceleration. Consider friction, neglect air resistance. So it's on a table, gravity is down, normal force is up. Are those balanced?
Doesn't it? Yeah, it's in the book.
Those should be balanced, but this one, the applied force, is clearly bigger than the friction force. How come? Rightward
Yeah,
acceleration.
do they have to the normal and wait for it to be there? It says neglect air resistance.
But it doesn't say neglect the fact that it's sitting on a table. It's not falling, it's sitting on a table, right? It's actually sliding across the table. Now, generally, Hannah, when we're doing questions like this, we generally just sort of ignore them because we
No.
know that they're going to be balanced. They have no bearing on the question. We'll just ignore them. But technically, from a standpoint of completeness, you should have them both. I'm not going to get excited about it after today. How about this one here? This time it's at a constant velocity. What's different? The applied force and the friction force are equal. So the up and down are equal to each other. The left and right are equal to each other. This is all coming back to you now, a little bit. College student rests the backpack on the shoulder. Pack is suspended motionless. That means that there's no motion, no acceleration. Balanced forces. Tension force balanced by gravity force. So one strap backpack.
He's just one strap.
He's, one of those cool kids.
Two strap.
Wow, that's just for, safety reasons.
It helps for posture, I think.
Probably, yeah. Skydiver descending with a constant velocity. Air resistance is considered, so these have to be balanced, right? Am I making sense, Zach?
Yep.
All good, right?
Yep.
Force applied to the right to drag a sled across loosely packed snow. Loosely packed snow is physics code for there's a little bit of friction. Right? You imagine yourself running through fresh snow, there's considerable friction. It's not easy. So we have normal force and gravity are balanced. We have an applied force forward. We have a frictional force that is less than the applied force. Do they have to be to scale? Like if the applied force was, say, 20 newtons and the friction force was 10, should it be half?
Yeah.
It should be. Am I going to get out my ruler and measure them? No. No. But technically they are vector diagrams, so they should be to scale. Having said that, should this one be bigger than that one? Yeah. I shouldn't have to tell or get a ruler out to see which one's bigger. Okay, here's the one that always causes some argument. A football is moving upwards towards peak after having been booted by the punter. After.
Rich, looks like dedicate this question to me.
Was I?
One of these punter questions last year you're supposed to dedicate to me.
I had a concussion. I don't remember last year.
I got it.
You got it right? Okay, this is known as the Steve DeRose question.
You have to change the
Patronizing, okay, would you? Yeah. Okay. So anyways, how come then, Steve, old knowledgeable one, how come that gravity is the only force? Is the ball moving upward? Yes, but how come I don't need a force if it's moving upward? Because objects in motion stay in motion. So the only force is that due to gravity. Right? You don't need that arrow because that arrow doesn't show motion. Those arrows show forces. Can it be moving up to the right and still have gravity down? Of course it can. What's that going to mean? It's going to come back down. And you don't need to go to a football game to know that when you kick a ball in the air, it's going to come back down.
I think it's the alternative we're looking at.
You think so? Oh, geez, there I did it again. Let's look at the last one here. A car is coasting to the right and slowing down. Neglect air resistance. Diagram the force upon the car. Last one. Weight force down. Normal force up. Coasting to the right.
No.
Zach, decipher the physics code here. No applied force, says Hannah. She's right. Friction force to the left, right? Okay. There's a few minutes left. If you have a question about the test, I strongly urge you to spend this time doing it now. Ask me now. Hang on to it. There will be a chance to revisit it. Don't just give up on things.
Make sure you don't forget.
That was just for me telling you what it was on, so I can change it right now.